Section 2.2, the 12 basic functions, domains, and ranges. All right, the first function we want to talk about is the linear function. Okay, and it has a parent function of f of x equals x. All right, and the domain, the values of x for which the function has a value, are all real numbers. Okay, and the range is also the values of the outputs are also all real numbers. Okay, so this is in some ways the simplest of functions. An interesting fact about this is this function is called a direct relationship and appears many times in nature, as you find when you study sciences such as biology, chemistry, physics, and others. This relationship shows up as the relationship between quantities in nature in many cases. Okay. The next function we want to talk about is the quadratic function. And the quadratic function has this shape. It has a parent equation of f of x equals x squared. All right, the domain, the values of x, are all real numbers. And the range of this function, the values of y for which this function has a value, are greater than or equal to 0. Okay. And an interesting fact about this is the graph of this function, called a parabola, has a reflection property that makes it useful in physics, in flashlights and spotlights, and other things too. All right, this function is called the cubic function. All right, and it has a parent equation of f of x equals x cubed. All right, the domain is all real numbers, and the range is all real numbers as well. Okay, and an interesting fact about this one is the origin is called a point of inflection for this curve because it changes its curvature at that point. To the left, it has a concave downward curve, which if you take your hand and put that in the shape of the curve over here, your palm faces downward, that's concave downward, whereas to the right, it's concave upward. Your palm would face upward at this point. And the point at which that curvature changes is called a point of inflection. Next, we have this function, which is called the reciprocal function or the rational function. And the parent equation for this is f of x equals 1 over x. The domain, the values of x for which this function has a value, are all values of x except x equals 0. There's an asymptote at x equals 0. The range, the output values, are also all real numbers except for y equals 0. There's a horizontal asymptote at y equals 0. All right. And an interesting fact about this one, this curve is called a hyperbola. All right. And it shows what's called an inverse relationship. And this also shows up in nature. All right. Generally, as x increases, y decreases, but more strongly than that, when x is doubled, y is halved. All right. And that's a rather rigid relationship that shows up in science. Okay, this function is called the square root function. It has a parent equation of f of x equals square root of x. It has a domain of all values of x greater than or equal to 0. That should actually say greater than or equal to 0. And it has a range of y is greater than or equal to 0. Actually, I got to change that. Okay, so x is greater than or equal to 0. Y is greater than or equal to 0. And an interesting fact about this one, put any positive number into your calculator and then take the square root. Then take the square root again, and again, and again, and again. Eventually, it will approach 1. So I invite you to pause this presentation and try that. Take any number you want and take the square root, take the square root again and again and again, and it will approach 1. And if you think about it, I'm going to guess you'll be able to figure out why. All right, what about this function? This function is called an exponential function. And it has a parent equation of f of x equals 2 to the x. Although, to be honest, this 2 can be any value. Okay. and 2 to the x. The x exponent is the business part of that. The domain is all real numbers, whereas the range is y is greater than 0, and not greater than or equal to 0, but just greater than 0. The x-axis is an asymptote for this function. An interesting fact about this, these relationships show up in a variety of examples in nature, including the growth of animal populations and in radioactive decay. Although in decay it would take a different shape. Okay, it would actually go like that, but it would be exponential in nature. All right, so these show up in nature as well. The next function looks like this, and it's called the logarithmic function. And it has the parent function looks like this, f of x equal to the log of x. The domain is all values of x greater than 0. The y-axis, it never touches the y-axis. It's not really an asymptote because it doesn't approach it from the other side. Well, I guess, yeah, the y-axis would be an asymptote because it approaches it but never touches it. And the range for this is all real numbers because this actually would increase and increase and increase. And an interesting fact about this, logarithms are exponents. And they were invented, I don't know who invented it, but somebody invented it, to make certain equations easier to solve and to make graphs easier to draw when one value is grows much greater than the other values. For example, if the y value grows at a much greater rate than the x, to compact the graph, we can draw it as a logarithmic graph. Okay, so in certain applications you will see that. And we'll learn about logarithms later on in this class. Next function looks like this, and it is called the sine function. It has a parent function that looks like this. Okay, the domain are all real numbers, and the range is between -1 and 1 inclusive. All right. And interesting fact about this, this is actually comes from the sinus cavities in your head. All right. All right. So yeah. So give that a read. Interesting. I didn't know that before I researched that, but this is interesting. From an Arabic manuscript, Arabs were terrific at mathematics, algebra in particular. Algebra is an Arabic word. And while the Greeks were really good at geometry, the Arabs were really good at algebra. And in that region of the world, the sine function was invented. In Arabia or in India, you know, if you research it, you find different results. But in that area of the world, the sine function was invented. So the Arabs were terrific at mathematics back in the day. So that's where it came from. All right, this one is called the cosine function, which is kind of the partner to the sine function. It has an equation of f of x equals cosine of x. The domain is once again all real numbers. The range is once again between -1 and 1, inclusive. And an interesting fact about this is the local extrema of the cosine occur at the zeros of the sine function and vice versa. So if you look back at the sine function, the zeros will be at x equals 0 and x equals here and here. And the zeros of the cosine function will be at the maxima, either positive or negative, of the sine function. All right, so check that out. Okay, the next function looks like this, and it's called the absolute value function. It has a parent function of this. The domain are all real numbers, and the range is y is greater than or equal to 0. Okay. And an interesting fact about this one is it has a corner right there. It abruptly changes direction. That doesn't happen in nature very often when you have an abrupt change, because nature is not herky-jerky, nature is smooth. But in this case, the absolute value function has a sharp corner. All right? That sets it apart from the other functions. Next function looks like this. It is called the greatest integer function. And it has a parent function of this. We're not going to deal with this too much, but it has a domain of all real numbers. Okay, closed circle there, but open circle there, so it kind of overlaps all the x's. Okay, whereas the range are just integer values of y. Interesting fact about this, it has a jump discontinuity at every integer value of x, okay? And these are also called step functions. Okay, this whole jump discontinuity thing we'll explain in a later section, although I think you've heard about it before. But anyway, these are called step functions. And greatest integer functions have applications in computer science. Because certain programmers and certain applications in programming take advantage of the greatest integer function. All right, finally, we come across the logistic function. It has an equation of this. And again, we're not going to deal too much with this in this course. It has a domain of all real numbers, and the range is between 0 and 1. Y equals 0 and y equals 1 being asymptotes. Okay, so there are two horizontal asymptotes, the x-axis and y equals 1. And in applications of biology and business, you'll come across this function with this equation. All right, we're not going to deal with it too much in this class. In fact, we're not going to deal with it at all in this class, but you will see it in certain applications. All right, so those are the 12 basic functions. Okay, now 9 of the functions of the 12, 9 have domains of all real numbers, which 3 do not. All right, so pause this video, look over the 12 basic functions, and which 3 do not have the domain of all real numbers. I'll pause and then come back. All right, what'd you come up with? One of them was the reciprocal function or the rational function. Okay, another one's the square root function, and the other is the logarithmic. Okay, the rational function has an asymptote at x equals 0. Square root excludes the negative values of x, and the log also excludes 0 and the negative values. So those have domains. Those do not have domains of all real numbers. Okay. Only 3 of the functions have ranges of all real numbers. Which of the 3? Pause and then come back. All right, one of the functions that has a range of all real numbers is the linear function. Okay, another is the cubic function. All right, and a third is the logarithmic function again. Okay, so those are the 3 whose ranges include all real numbers. All right, now let's talk about intervals where the functions are either increasing, decreasing, or remaining constant. And we want to write these in both interval notation and inequality notation. So first of all, where is the graph increasing? Well, I see it's increasing right here in this part. Okay, and for x values, this arrow indicates that it goes off to negative infinity. So from negative infinity to x equals -3, it is increasing. So we're going to write it as that. Okay, closed, open bracket, meaning that it never really touches that. You know, you never really get to negative infinity, but the closed bracket indicates that it does. Okay, so, and we're going to include the points to be inclusive. Okay, so that's why we're going to use a closed bracket. All right, another interval where it's increasing is right here, from x equals 1 to x equals 4. And so we're going to union that because we're going to include both 1 to 4 and again, when we have points here, we're going to use the closed brackets to represent inclusive. Okay. All right, let's write this in inequality notation. The first interval being represented as such. Okay. So x is between negative infinity and -3, non-inclusive on the infinity side and inclusive on the -3 side. And then between 1 and 4, inclusive on both ends. Okay, so that's how we can write that in inequality notation. Okay, where's the function decreasing? Well, it's decreasing right here, in this interval right here, and that's from x equals -3 to x equals 1. And we're going to use closed brackets for inclusive. And then in inequality notation, we can write it like this. Okay, x is between -3 and 1, inclusive on both boundaries. Then the graph is constant right here when x is 4 or greater. Okay, so 4 to positive infinity. All right, open bracket on the infinity side. And then in inequality notation, we can write it like this. X is greater than or equal to 4. Okay. All right. Okay. That's for this function. Now, let's do it for this one. In fact, I invite you to pause this and see if you can write these, and then come back and we'll go over it. All right, so the graph is increasing. Here's one interval where it's increasing. Okay, and that's 1, 2, 3, 4, from -5 to -3. From -5 to -3. It's also increasing in this part right here from, where is it, from 4 to 5? Oh, sorry, I missed one right here. From -1 to 1. Oh yeah, right there. Missed that one. And then there's the 4 to 5 part right there. Okay, so we have three, one right there, one right there, and one right there. All right, and then in inequality notation, we could write it like that. X is between -5 and -3. X is between -1 and 1, and X is between 4 and Now let's talk about the domain and range of a graph. Okay. Now remember the domain is, and we're going to write these in both interval notation and inequality notation. Right. Now the domain is our values of x, as you recall. So I'm going to have an imaginary vertical line that's going to start at the left and move to the right until we encounter the graph. Okay, and that's right here at x equals -2. All right, so it begins at -2 and has values all the way to positive infinity from there. All right, so I'm going to write it in interval notation like this, where the closed bracket indicates closed, inclusive, -2, and with infinity it's always open bracket because you never actually get there. So that's what it is in interval notation, and then in equality notation we can write it like this. You could also write it as -2 is less than or equal to x is less than positive infinity as well. Okay, you could write it like that. I'll write it like this. Either way is okay. Okay, the range are values of y, so I'm going to have an imaginary horizontal line that's going to start down there and bring it up, and it encounters the graph right here at y equals 3, inclusive, and then goes to positive infinity from there. So it's going to look like that. In inequality notation, we can write it as such. And once again, you could have 3 is less than or equal to y is less than positive infinity there as well. Either way. Okay, let's do this one. Now, so if we start for the domain, start over here, where does it first encounter the graph? It first encounters it at x equals -2. And then from then on, it goes to positive infinity, as indicated by those arrows. So the domain will start at -2 and go to positive infinity. And if I write that in inequality notation, I'll write it like that, greater than or equal to include the -2. For the range, these arrows indicate, here it indicates that it goes to negative infinity, to positive infinity, Okay, so the range here, I can write it like that. And in inequality notation, we can write it like that. Okay, or we could simply say all real numbers. Okay, for both. All right, so that's this one. All right, let's try this weird looking function here. This is actually a function, right, by the vertical line test. The domain, starting at the left and right here, it first encounters the graph right here at x equals -2. All right, and as we keep going, it keeps touches it until here. Oh, that open circle includes means that it doesn't include x equals 3, but it includes everything else. Okay, so for the first part of the domain is this one right here, from -2 to 3, non-inclusive on the lower boundary. Inclusive on the lower boundary, non-inclusive on the upper boundary. And then we have from 3 to positive infinity. In inequality notation, we can write it like that for the first part, and that for the second part. Okay. For the range, starting here, bringing up a horizontal line, that dashed line actually indicates an asymptote at y equals -4. So the graph never really gets to -4. So that's going to be a non-inclusive boundary. It goes up until y equals -1. Kind of skips over that, right, because of the open circle. And then has values all the way up to y equals 3. All right, so there's two parts to this also. From -4 to -1, non-inclusive on both boundaries. And then from -1 up to a positive 3. Non-inclusive on the -1, inclusive on the 3. Okay? In inequality notation, there's the lower part of it, and there's the upper part of it. Okay? All right, as a final example, we had this weird looking thing. This is actually called a piecewise function. All right, I invite you to stop, pause the video here, and write the domains and ranges, domain and range, in interval notation and in inequality notation. All right, as far as the domain goes, starting over here, that arrow indicates it goes to -infinity. So at -infinity all the way up to x equals -1, non-inclusive. So we can write it like that. Okay, and then we skip over to x equals 0, inclusive, all the way to x equals 4, non-inclusive. And then it skips to x equals 5, inclusive, and then it goes to positive infinity from there. So we write it like that. In inequality notation, there's the first part. There's the second part. Be careful with the less than or equal to signs and the less than signs. And the last part would be that right there. All right, for the range, this arrow indicates it goes to -infinity. So does this. So that the lower boundary is -infinity. And if I just take that horizontal line and just keep moving it up, okay, it encounters the graph 3 times here, but that's okay because multiple inputs can go to the same output. And it keeps on going, keeps on going, keeps on going until y equals 6. And that's the last time that this function has an output. Okay, so even though it intersects the graph 3 times here, it doesn't matter. The range are values of y for which there is an output. For which there is a value of y. And that's anywhere from -infinity all the way up to positive 6, inclusive. So I can write it just like this. Okay, I don't have to break it up into parts. It's just all the way from there to there. All right, and then in inequality notation, we could write it like that. Or we could just simply write it as y is less than or equal to 6. That would cover it as well. Okay, so those are some things about the 12 basic functions and domains and ranges. All right, so go have some fun working on the practice problems.